Good afternoon, everyone. My name is Elena Surovyatkina. I'm happy to be here, and thank you very much, organizer, to inviting me to your very interesting conference. I'm going to discuss with you and show my recent results on the most important, one of the most important climate phenomena in India, Indian summer monsoon. My lecture consists two parts, and I will start with topic from critical phenomena to prediction of Indian summer monsoon. It would be part one. And then on a second part of my presentation, I'll show you methodology which I use for forecasting monsoon onset and withdrawal. So let us begin. To plow or not to plow? This is a question for this farmer. When will monsoon come? Farmer already has debts and it's struggling to feed himself and his family. A wrong decision could potentially lead to further hardship for him. When will monsoon come? Temperature in his region in central part of India in Maharashtra state in 2016 was 51 degrees. And this farmer has to have decision to plow or not to plow. So it happens annually with extreme droughts before onset of monsoon, heavy rain at the beginning, and damaging floods at the end of monsoon season. Why is monsoon so difficult to predict? What are major limitations to achieving better prediction? The history of numerical weather prediction began 100 years ago. Before that time, meteorologists performed forecasts by looking for similar weather pattern from the past records and then extrapolating it in the future. In 1920, Lewis Fry Richardson attempted to calculate by hand for 6 hours the weather over 2 points in Germany. Here. The calculation 6 hours forecast took for him at least 1,000 hours during 1910. It's a remarkable achievement considering the calculations were done by hand. And while Richardson was serving in a war during this period of time in northern France, unfortunately, the first forecast failed. However, Richardson managed to outline the problem correctly and define numerical algorithms still used today to integrate differential equations. Nevertheless, he was moderately optimistic in his concluding remarks. Perhaps someday in dim future, it will be possible to advance the computation faster than weather advance. But that is a dream. So this is the beginning of era of weather forecast. What happens next? First calculation for 24 hours forecast took ENIAC. This is a first computer, nearly 24 hours to produce 24 hours. And it's interesting to notice that actually female, have been instrumental to working on this forecast because men at that time have been on a war. And actually, at that time, term computer refers to a person doing the computation by hand and using the first calculators. So This is impact of female in weather forecast, and this was first calculation. The recent 70 years show exponential growth of computer power. Is a problem of numerical prediction solved already? So let me say, let's go further and we will see. So in 1961, Edward Norton Lawrence was running computer model to perform weather prediction. He ran his program twice and get to trajectory. The second time, he entered the initial condition 76.8 from printout instead of entering decision 76.853. The result was surprising. From nearly the same starting point right here, two trajectories are closest to each other for 6 days only. But then Lawrence saw that his computer weather produced a pattern that grew further and further apart until all resemblance disappeared. And you can see trajectory going in different way. So finally, he got completely different weather scenario. Of course, he was very disappointed about this problem, and but after 2 years, he realized that a very small change in initial condition in a system of a partial differential equation of weather forecast. He realized that very small initial condition could create significant different outcome. So the sensitivity initial condition is another fundamental problem of weather forecast model. Lawrence named it butterfly effect, meaning when butterfly flutter its wing in one part of the world, it can eventually cause a hurricane in another. So, and this problem actually is not has not solved yet. So what is the same problem every meteorologist have in every 3 hours producing forecast? Actually, two trajectory in real forecast models that used today over the world in India, in US, whatever over the world, actually only 2 days reliable forecast. But then trajectory going in different way. And this is a kind of state of the art in meteorology, how to make better initial condition. But actually, this is fundamental feature of a system of partial differential equation that used for producing weather forecast. And no, let me say, other way to make different way initial condition to solve this problem. So this problem is still today. So that means reliable weather forecast, whatever it's producing from any countries, would be only 2 days. Even though artificial intelligence systems that nowadays very popular to produce forecast, weather forecast, the problem is that computer became faster, it's calculate faster, but system of equations the same. So whatever how fast system would be calculate, the problem of initial condition remain there. So 2 days, what any other system, 2 days reliable weather, no more. So fundamental problem lies in a chaotic nature of special differential equation used to simulate atmosphere. It's impossible to solve this equation exactly. Small error in temperature, wind, or other initial input grow with time. Therefore, numerical weather prediction method only obtain an approximate solution. So, major limitation in numerical weather prediction. Numerical weather prediction has a limit to forecast weather up to 5 days in future. Extremely small error in temperature, wind, or other initial input give numerical model will amplify and double every 5 days, making it impossible for long-range forecast. If you find long-range forecast or so-called seasonal forecast, that means this is an average forecast. That means if it's average, it's never able to produce droughts and floods. It would be very average weather that actually not so interesting for people, because this is no extreme. It's impossible to predict any extreme weather event. Existing observation network have poor coverage in some region. For example, over Pacific Ocean, with introducing uncertainties into the raw initial state of the atmosphere. These uncertainties limit forecast model accuracy to about 5 or 6 days in the future. The limitation of current model prevent further progress. A new strategy is desperately needed in weather and climate sciences. And I completely agree with Stevens and Bonnie in this statement. We need to go further and to find another way to make progress. So another problem, why it's so difficult to forecast monsoon? The problem is the following. So let me briefly introduce intertropical convergence zone notion. Probably you know this, but the idea is that in intertropical convergence zone, this is an area around equator where two pattern of winds merge in some area. And you can see this is a wind going from the north, and this is a wind going from the south, and around the equator, this convergence appear. So the because our axis of Earth have inclination 24.7 degree. It appears that when intertropical convergence zone following by the maximum solar radiation, its position varies seasonally. So that means in summer in South Hemisphere, it would be maximum solar radiation right here, actually on the northern part of India. It's a little bit not good map here. Northern part of India. And it moves north in the northern hemisphere summer, and it's going south in the northern hemisphere winter. So, and in you can see difference. So this is July and this is January. And position of intertropical convergence zone, movement of intertropical convergence zone, speed speed of this movement. This is the main characteristic of this process, and it's all every year going in different way. So this is why it's very difficult predict the beginning, monsoon onset and withdrawal. So this is one more problem in forecasting. And then, so this is pre-monsoon, May in Eastern Ghats region and Western Ghats region, and this is monsoon season. We can see difference. So more problem for forecasting monsoon. Let me show you an example. So this is statistics over the period of observation from 1951 to 2016 when we published our paper. So on this plot you can see onset of monsoon, and this and isochron show the beginning of monsoon in different part of India. The problem is that monsoon start in different part in different time, and this is a very special temporary big problem. So if we calculate from 1951 to 2016, we can see that monsoon in central part of India, right here, 20 north, 80 east, monsoon could start from 4th June or 29th of June. 1 month variability of the beginning of monsoon. And if we see, if you look on withdrawal forecast, it would be the same, not forecast, actually, fact. Withdrawal of monsoon registered by Indian Meteorological Department and both figures. We can see that it could happen from central part of India from 17 September to 29 of October, more than 1.5 months. So this is why it's very difficult to predict monsoon. So Indian Meteorological Department forecast monsoon for Kerala state, and but for Kerala state only. And here you can see on this slide the condition for onset of monsoon over Kerala. IMD produced this forecast 2 weeks in advance and on 15th of May. So, and actually, the forecast of IMD for Kerala is good. And they doing well in this forecasting Kerala. However, what is the problem? Why it's impossible to go further? So to forecast all every state in India. Why it happens? Why it's no progress since 2005 in prediction of monsoon onset? The problem is that this only valid for Kerala region, south tip of Indian subcontinent, Bay of Bengal from one side, Arabian Sea from another side. So all these conditions only valid for Kerala state. It's impossible to apply this condition for any other state because it would be different condition. So this condition works only for Kerala. This is why it's impossible to go further. Once we accept our limit, we go beyond them, according Albert Einstein. Let us try to find out some kind of universal definition for onset of monsoon for every state in India. and we're going slowly from first part to next part of next lecture today. So let us look on this map. This is the temperature over Eastern Ghats region. This is the data, Insepankari analysis data for period of observation. For period of observation, I'm not able to see, okay, if I make it, for 30 years, I guess so. So, and you can see, it's called climatology in meteorology. So, and we can see the transition, this is pre-monsoon season, and then 150, that's mean 1st of June. And then we can see smooth transition to monsoon. Transition to monsoon season happens gradually, according to climatology. And any other models use the same way, assuming the transition to monsoon in India actually gradual. However, let us use the same plot and put on this plot data, for example, 2016. What we can see on this plot, you can see, looking on individual year, it shows sharp transition here. This discovery allows us to apply theory of critical transition. So I propose to establish two stable states in critical transition, pre-monsoon and monsoon, and between them critical transition with critical value of temperature, and determine value of critical threshold right here. Monsoon season begin once temperature crossing critical threshold. And this is for central part of India, Eastern Ghats region. So we found pattern, and let's see what we can do with this pattern. If we looking closely to this is onset of monsoon, but if we're going to transition from monsoon to post-monsoon, we can see actually gradual transition. And what is the physical difference between this transition, abrupt transition, and this smooth transition? So abrupt, let me show you an example. This bottle has a stable state. This stable state. If I put this, if I force this bottle, it will be fluctuation appear. And then more forcing, more fluctuation. Finally, this bottle from one stable state going to another stable state. And this kind of transition, it's called first order of phase transition. And I show you on the next slides. So this is an abrupt transition. The bottle cannot be in between. It's going to another stable state. But what does it mean, this smooth transition from monsoon to post-monsoon? It's called second order phase transition. If I use ruler and I will start to squeeze this ruler, what happens? It's going up or down. And this is smooth transition from one stable state to another stable state. In our case, in this one. So let's go further. What we can do with this finding? This is persons who actually create a theory of bifurcation, and after that, phase transition theory. Henry Poincaré introduced the notion of bifurcation. And Alexander Andronov actually use this knowledge and prove the theorems in different field in the physics and for solution of physical problem. And then Lev Landau also Lev Landau create phase transition theory. What is the difference, let me say, between all this theory of bifurcation and theory of phase transition? Actually, it's going, there is the same subject, like critical transition, but considered in different discipline. So in mathematics, from beginning of Poincaré, but then in physics, to apply physical problem using this transition. So let us see just very short definition. A bifurcation of dynamical system is qualitative change on its dynamic producing by varying parameter. But in this is mathematical definition. And actually, one can also use that to understand that what is a bifurcation? Bifurcation when system lose stability. In this case, when it's abrupt transition, it's lose stability and going to another stable state. And to exchange stability, no any other way. So, and different kind of bifurcation anyway going to this result. In physics, phase transition is a physical process transition between one state of the meaning to another. So actually, the same problem just treated in a different way. Mathematicians doing their work to prove this theory, to, let me say, extend number of bifurcation. In physics, application of this theory for many, many different problems in physics. So, and then I give you references of very very important books in this subject, and you even though can download PDF book by Landau Lifshitz. So I will put it in system to download my presentation. So what we how to describe this problem? This is a problem with abrupt transition. So, as well known, this is a equation of nonlinear oscillator. It's well known that number of minima of potential energy profile in nonlinear oscillator determine the number of equilibrium state. So, if we introduce potential energy profile in this way, and we use first term A like control parameter, we can see that if A greater than 1, we have only one stable state. If A is equal to 1, the system going to change to lose stability, and between 0 and 1 it would be two stable state here, another stable state appear, and then if A less 0, it's going to finally one state here. So how to make this, to understand what happens in the system. For that, we use bifurcation diagram right here. So here, horizontal axis show parameter values of parameter A, but Xi show there is a variable in this equation. And to calculate every point here, you have to use initial condition and then waiting for a long time when system actually approaches stable value. And if you're going to produce bifurcation diagram, you have to be very careful to make this kind of scheme. This scheme show you everything about system. You can see that here is the one stable state, here there's another stable state. So this is a B stability between them, non-stable state. And then we can see the system here lose stability. It's called sudden node bifurcation. And then here also exchange of stability. It's called transcritical bifurcation. So let's go further. If we're going the same, but potential energy profile show us only transition from one stable state to two stable state. And we can see if we consider B as control parameter right here, we can produce bifurcation diagram here. And it would be exchange of stability. And it's called pitchfork bifurcation. So actually, B is a control parameter because it's called second order phase transition because B is under second order of expansion. But in previous case, it's called first order phase transition because A is zero order here. So then every system, every process have always include noise. And what happens? What happens if system here, I'll show you fluctuation here. If B greater than zero, then there is a potential energy profile. It's not, it's deep, and here actually not so strong fluctuation. But when system go undergoing bifurcation, and this pitchfork bifurcation case, we can see potential energy profile became wider, and then we can see that fluctuation growing. And then when it's finally reach two stable state, we can see the variance of fluctuation became less. So similar picture on first order phase transition. At the beginning, it's smaller. Then when system going to lose stability, it became stronger fluctuation. And then again, when it's reach another stable state, enhancing in fluctuation became less. So, and this process that I described before, it's called critical fluctuation because this critical fluctuation appear close to the critical point. And actually, Kurt Weisenfeld shows that critical fluctuation going indefinitely high into critical point. In my work, you will see that critical fluctuation actually saturated closer to the critical point. And this is proof of this increasing fluctuation close to the critical point. You can see on example of second order phase transition that away from bifurcation point, variance of fluctuation proportional to variance of noise. That means like linear regime. system have been forced and then respond proportionally. This is away from bifurcation point. You have a linear regime. What's going further? At approaching bifurcation point in this way, approaching bifurcation point, variance of fluctuation increases and immediate vicinity of bifurcation point, variance of fluctuation actually proportional to standard deviation. So this is so it's not going indefinitely. It's going to the very high fluctuation there. So fluctuation growing close to the critical point. But one more phenomena also appear in what I showed you before. It was quasi-stationary case. That means every point in this bifurcation diagram have been treated separately. Every point which you use calculate many times and to reach stable point. Here it's called dynamical bifurcation. That means control parameter here is actually changing in time. And then if parameter changing in time, you can see actually this bifurcation point appear here in quasi-stationary case. But when parameter changing in time, it's going to be delayed. It depends on the speed of the rate of control parameter, epsilon. And you can see depending on the epsilon value of parameter when system crossing critical threshold would be different. And this is the same, but when control parameter decreasing in time. And we can see that system going another way, but in this case, it's actually depending not on initial condition, but depending, actually, this it's depend on initial condition, but this depends on the rate of change of control parameter. So this is these instruments that I presented to you, I used in my research over 30 years in different fields. Starting from medicine, problem of arrhythmia, and then liquid crystal dynamics. This we made in Oxford with John Ockendon, Apala Mozardar, Peter Howell, liquid crystal dynamics. Then thermoacoustic instability we're doing with Sujit in, we have done many papers with Sujit in IT Madras. So, but these my instruments. And I'll show you how to use this instrument to solve problem in different fields. But this instrument, universal. Once you can see sign of critical transition, you can work and you can get result. So critical phenomena, finally, like resume. Pre-bifurcation growth and saturation of fluctuation. And this phenomena we are going to use in methodology to forecast monsoon. Moreover, pre-bifurcation rise and saturation of the correlation time of fluctuation. Actually, this, my work, actually after that, it was renamed like slow down. But okay, but I prove that pre-bifurcation rise and saturation of correlation time in fluctuation there. And you will find in this paper. And then rate-dependent critical phenomena. This is a liquid crystal dynamic subject, and you could see all mathematical aspects that use my collaborator from Mathematical Institute of Oxford. So, how to use this? For example, when fluctuation growing, actually it's impossible to say when system reach critical threshold. Because when you're looking on the data, you never see this, it's impossible to estimate where is it, because it's depending of rate of change of control parameter, it depending of how far away system from critical threshold, etc. So fundamentally impossible to predict something when you have data and trying to estimate when this transition happens. However, in technical system, it's very useful instrument. Why? Because, for example, in this turbine, this is a very big problem in hydro turbine. When fluctuation appear and it's growing, it became damaged. And this is a very common case in many different system and engineering. We can stop fluctuation. When we see that fluctuation rising, we can stop system, but in technical sense. In climate, we cannot stop anything. And this kind of projection I never doing because it's actually not a science. It's just management. So, but in technical system, it's very powerful instrument to work with. So in general, phenomenon of dynamic stability exchange depends on the multiple factors, such as nature of bifurcation point, initial value of control variable, the presence of interference, noise. Of particular importance is the rate at which the control parameter crosses its critical value, which we assume to be slow compared to response time of the system. So this condition you can use for solution and instruments for solution many problem in technical system. So to conclude first part, pre-bifurcation noise dependent and rate dependent phenomena might be used as a precursor of impending bifurcation for dynamic and stochastic transition. Appropriate choice of precursors might lead to prevent impending catastrophe. The evaluating the role of dynamic and stochastic factors might be also useful for assessing vulnerability technical system. The preliminary investigations suggest that heat-hetero neglect dynamic effect induced by small parameter, such as the rate of change of control parameter, I'm talking about dynamic bifurcation, might have a crucial impact on abrupt transition in system of different nature.